Hello everyone, welcome to the lecture number 7 of the rotational motion. Today's topic is rotational energy. So we'll see what is rotational energy. Suppose this is the axis of rotation and one body of distributed mass is rotating with respect to this axis like this with angular velocity of omega, and let's say the moment of inertia for this distributed mass body is I. And this distributed mass body constituted of many small masses m1, m2, m3 till mn. So each of these masses, small masses, is rotating with respect to this axis with the same angular velocity. Now let's look at this body from the top. So let us draw a top view of this body. Suppose like this, and this is the axis which is right now, top view means which is right now perpendicular to the plane, the axis, and it is rotating like this. This is top view. Let's say the masses are kept m1, m2, small masses are there till mn. Now the kinetic energy for mass 1 or m1 is half of m1 into v1 square. Kinetic energy for mass 2 is half of m2 into v2 square, where v1 and v2 dot vn, those are the velocities of these small masses. Now if it is rotating with respect to this axis with angular velocity of omega, what is v1? v1 is the distance from the axis into omega. If the distance from the axis for mass 1 or m1 is r1, we can tell that the velocity is going to be r1 into omega. Velocity for m2 will be perpendicular to the distance vector r2, but the velocity magnitude will be r2 into omega. So for all these masses, small masses, the angular velocity is going to be the same because they are all rotating with respect to this axis. So for mn, if the distance is rn, it is rotating with vn velocity. So vn will be rn into omega. So we'll put that. We'll put the value of kinetic energy 1 here. Half of m1 into r1 omega square. Similarly, for kinetic energy half m2 v2 square, we can write m2 into r2 omega square. Similarly, for nth particle, it will be half of mn into rn omega square. So right now this distributed mass body total energy will be the sum of all small individual kinetic energies of all these particles m1, m2 mn. So Ke total will write, that is sum of all these energies. So we'll write half of m1, we'll write r1 square omega square plus half of m2 r2 square omega square plus half of mn rn square omega square. So we'll take omega square common, or we'll keep omega square outside. So it will be m1 r1 square plus m2 r2 square plus plus mn rn square multiplied with omega square. Now see, this is the sum of the mass multiplied with the distance square from the axis. This is the summation. This summation is well known to us, that is the moment of inertia for this body. So half of I into omega square, that is the kinetic energy. Now we will not call this kinetic energy, we will call it rotational kinetic energy or rotational energy for a body, for a distributed mass body which is only rotating with respect to this axis with angular velocity of omega. So if one body is having moment of inertia of I with respect to this axis of rotation and it is rotating with angular velocity of omega, we'll call it half of omega square as the rotational energy for that particular body. Rotational energy. See, it is very similar to our linear motion or translational motion. Translational motion, what is the kinetic energy or linear kinetic energy will tell half of mass into v square or half of mv square. But in the case of rotational motion, the equivalent of mass is moment of inertia and equivalent of velocity is angular velocity. So see, it is very similar. So let's say this is a disk which is rotating with respect to z axis with angular velocity of omega. Its mass is given as m and the radius of this disk, solid disk, is given as r. Then if I tell what will be the kinetic energy for this rotating disk, if it is rotating, then the rotational kinetic energy, Re will be half of I into omega square. Now what is I for this disk with respect to this axis? See, I is half of mr square into omega square. So mr square omega square by 4, that is going to be the rotational energy for this disk. Now similarly, for a ring, it is connected to this axis via massless spokes and is rotating with respect to this axis with angular velocity of omega. Same angular velocity of omega, mass is m, radius is r. So what is going to be the rotational energy for this ring which is rotating? Half of I omega square, but here I is mr square into omega square. So we'll write m r square omega square by 2, that is the rotational energy for this ring of mass m and radius r. Now see, if the mass is high, in case of translational motion and it is moving with velocity v, its kinetic energy we call it half mv square, and if the another mass of 2m is moving with same velocity, its kinetic energy will be half of 2m into v square. So it depends upon this mass. So similarly here also the rotational kinetic energy will depend upon the moment of inertia. So more the moment of inertia is, more torque we need to apply to stop it. So more torque or more effort will be needed to stop this ring from rotation compared to the disk rotating with the same angular velocity. Now we'll go to the work energy theorem in rotational motion, purely rotational motion. So work done in the case of linear motion or translational motion, you know that it is force into displacement. Force into displacement. In the case of rotational motion, the work done is torque into the angle of rotation. Torque into angular rotation, because torque is equivalent to the force and theta, there is the angular displacement or angular distance, that is equivalent to the displacement here in the case of translational motion. Now let's say there is a m mass here and it is rotating with respect to the axis in anti-clockwise direction with angular velocity of omega. Its distance from the axis of rotation is r. Now say at an instant it is rotated by a very small angle d theta. Now what is going to be the displacement for this mass? R into d theta, that is going to be the displacement for this mass, this displacement, R into d theta. Now suppose I am applying F force on this mass at a distance r from the axis of rotation. It is purely rotation motion. It is completely rotating. Now what is going to be the small work dW to rotate it by small angle d theta? You know from the work done, it is F dot S. So here in this case, F and S, the direction is same, so it is going to be the F into S only. So what is S here? If I rotate it by small angle d theta, the displacement is r d theta, F r d theta. Now see, with respect to this axis of rotation, F into r, this term is the torque with respect to this axis or with respect to this point, is the torque. So we'll write it T into d theta, small work dW. Now total work will be similarly integration of T d theta from suppose 0 to theta. So this is the work done in the case of pure rotational motion. It is very similar in the translational motion case, F ds from 0 to S, that is the value of the work done. Now we know that in the case of translational motion, force is equal to mass into acceleration. In the case of rotational motion, equivalent to mass is moment of inertia and equivalent acceleration is angular acceleration. So I into alpha. Alpha is rate of change of angular velocity. Rate of change of angular velocity omega. So you can write it alpha is equal to d omega dt, rate of change of angular velocity. So we can write d omega also like this, d omega by d theta, multiplication of d theta both in the numerator and the denominator. D theta by dt we can write. See, this term is a rate of change of angular displacement, d theta by dt. So we can call it omega. So see, it is becoming omega d omega by d theta, that is alpha. So now you know that small work done is tau into the d theta, and tau or t you can write I into omega d omega by d theta into d theta. So just replaced this part here. So we will get that I omega d omega is basically the small work done dW. Now net work done, integration of I omega d omega. If the angular velocity changes from omega 1 to omega 2, then net work done will be W. So we can write I will come outside, because for a particular body I will be constant, so it will come outside of the integration, and we will only integrate omega d omega. Omega d omega integration is omega square by 2. We will put the limit from omega 1 to omega 2. It is changing the angular velocity from omega 1 to omega 2. We will get that it is half of I omega 2 square minus half of I omega 1 square. Now see, this is the work energy theorem in the case of rotational motion. Net work done will change its rotational kinetic energy. In the case of work energy theorem in translational motion, we have seen that net work done will change the kinetic energy of the particular body. Here we can tell that net work done will change the rotational energy for a particular body, or rotational kinetic energy for a particular body. That is the work energy theory. So net work done will eventually change of rotational energy. Now we'll solve a problem and we'll be able to understand it in very clear way. And note one thing, that we are talking about purely rotational motion. There is no translation involved. And after we understand all these topics of rotational motion or pure rotational motion, we will go into the mixed motion where there will be rotation as well as translation. So right now we will consider it only as a pure rotational motion. Let's solve one problem. Let's say there is a rod which can rotate with respect to this pivot point. The mass of the rod is m, the length of the rod is L. It can fall freely under gravity, but it will not have any translational motion because this pivot is restricting the degree of freedom for the translation. So it will only be able to rotate in this direction. So due to the gravity, it will fall like this, and it will eventually land like this. So what will be the angular velocity when it will fall on the ground? When it will fall on the ground. We can use simple work energy theorem to find out the final angular velocity when this rod will fall like this. Right now it is completely vertical position. So this is 90-degree angle. Now see, from the work energy theorem, we know that total work done by all the forces or all the torques will change, will write delta of rotational energy. That means we can write that rotational energy final minus rotational energy initial. Total work done. Total work done. So see, initially the rod was at rest. So initial rotational energy will be 0. So half of I into omega square will be 0 because omega was 0. So that means the net work done will eventually give it the rotational energy when it will fall on the ground. So this is 0 because the initial angular velocity was 0. Let's assume that final angular velocity will be omega. So what will be the rotational energy for this rod of mass m and length L? Half of I into omega square. We have to find out this omega. I for this rod with respect to one extreme end, if it is rotating with respect to one extreme end, you know, if the mass is m and length is L, the moment of inertia is m L square by 3. So we'll just put that. Half of m L square by 3 into omega square, that is equal to net work done. So what is doing the work on this rod? Gravity. So due to gravity, right now it is having some kind of potential energy. When it will fall on the ground, its potential energy is becoming 0. So net work done by the gravity, that is basically potential energy only at this point. That is potential energy change. Right now, what is the potential energy at the vertical position? Its center of mass is lying at L by 2 height. And finally, its center of mass is falling on the ground. So with respect to the ground, the potential energy change is potential energy initial minus potential energy final. So what was potential energy initial? Its center of mass is at L by 2 distance. So it is mg into h, mg into L by 2, because the center of mass is falling by amount L by 2 when it is hitting the ground. So that is the net amount of work done, mg L by 2 minus 0. Here the potential energy is 0. So you can write mg into L by 2, that is the net work done on this rod. That is equal to half of m L square by 3 into omega square. Right now from this relation we can find out the value of omega square, or omega eventually. So 2 will cancel. So it is m will cancel both the sides. 3g by L. So omega square is 3g by L. So omega will be root over of 3g by L, that radian per second, that is going to be the angular velocity of the rod when it will hit the ground. So next one problem we will solve, that is one rod is rotating with respect to its center of mass with angular velocity of omega. The mass of the rod is m and length is L. Another disc is rotating with respect to this axis with the same angular velocity omega. The disc mass is m and its radius is given as L by 2. Find out their ratio of rotational energy. It's very simple. They are all rotating with the same angular velocity omega. So the ratio rod by the rotational energy of the rod by rotational energy of the disc is going to be half of I rod omega square by half of I disc omega square. See, omega square by 2 will cancel. So that means the ratio will be basically the ratio of their moment of inertia only, I disc. Now what is the moment of inertia for this rod if it is rotating with respect to its center of mass at the middle point? M into L square by 12 by that for the disc it is rotating with respect to the middle point and the axis is perpendicular. I disc, that is the moment of inertia of the disc, is m into r square by 2, but here r is given as L by 2, so m into L by 2 square by 2. So it is very simple right now. M will cancel, L square will cancel, so it is basically 1 by 12 by 4, 1 by 8. So it's basically 8 by 12, that means 4 2s, 2 by 3. So the ratio of the rotational energy is 2:3. I hope you understood.
Now solve these three problems.